Hello fellow nerds and welcome to Nerd Chat. I'm your host Steven, Nick's your studio producer in the back, and today I'm joined by Mike Mattera.
Hi Steven, thanks for inviting me.
Thank you too for being with us tonight. Mike is a CNC specialist and machinist as well as a content experience designer for Autodesk. So how are you doing tonight?
Doing good, doing good. Glad to be here, and I've been looking forward to this.
So let's get into the questions then. What has your career life been like? How did you get to where you are now?
Well, as you can tell from my gray hair, it's been a long journey. But I started off in a machine shop. I was running machines, and I kind of progressed my way through teaching the new guys how to do it and worked my way into the programming department. And the company I worked for actually built CNC machines. So we were actually making parts for the machines that we were running, which was kind of cool. Then I got promoted into the applications engineering department, which is where you actually go out in the field and teach new customers how to use those machines. So that was a good experience. And then I left that company and went to work for a CNC control company. They developed their own CAD/CAM system, so I developed some computer experience along the way. And again, working with customers, helping them solve problems and figure out their machining goals and achieve them. And then I went to work for a company that made CNC machines again, and these were more high-end multi-axis machines. And all along the way I've been using CAD/CAM systems because that's really what makes a CNC machine run. So from there I started my own company. I produced video training content, did that for about 12 years. And then I got recruited by a company called Autodesk, wonderful organization. They have all different types of software, but their main focus is CAD/CAM. And I do the content for their Fusion 360 product. I'm the CAM content expert, which is a lovely thing to be called, the expert. But anyways, essentially I write the manual and I do the little tool tips that pop up in the software. And I love it. It's a great job, it's a great company, and we're right here in Portland.
So what did you study in school?
Well, really, there wasn't anything specific in school that I went through. I took a lot of courses, you know, as my career started to develop. As I was out in the world working, I would take maybe a programming course or take a course in how to use different CAD/CAM systems. And of course, with the companies that I've worked for, that's been an educational experience. They've been sending me to training for different things all along. You know, they would send me to training for this control or that machine, and it's been that kind of a journey. You know, any place that you ever go to work, always find the old guy and hang around with him, because I tell you, some of the best things I've learned were from the guy that was in the shop, showing you the cool little widget tool that he's got in his toolbox and how it works and what he can do with it. So it's been that kind of a journey of, you might say, hard knocks or on-the-job training for most of the truly important things, I'd say. But, you know, there are courses available today that weren't available before because the proliferation of CNCs becoming less expensive and CAD/CAM systems and PCs being so available that you can go to any community college and get a 2-year associate's degree and learn about CNC programming and learn about, you know, running machines or tool and die work. And those are all really great careers, and they're positions that are in very high demand right now.
So you kind of touched on there a bit. How did you learn your machining skills?
Well, again, you know, a lot of it was just being in the shop and having people, you know, guide you down the path. Initially, I started off as a button pusher. You know, somebody set up a machine, and you know, you put in the part and push the button. So it was a lot of keeping your eyes open and paying attention to what was going on. The way I got into the programming department was, they came out, loaded the program. I was setting up the machine, and I went through the program line by line, and I found something that was wrong. And most guys would go say, "Hey, you know, I ran it, it stopped. There's something wrong with the program." I went in and said, "There's something wrong with the program. This line is wrong, and this code should be this code." And they went, really? Okay, here's a set of keys. You're now the lead man for the department. So that's how some of it came about, was just by paying attention to the people who knew what they were doing.
So what did you find the most challenging to master?
Oh, wow. Boy, that's a tough question. The most challenging to master. You know, every day you find new problems, and it's always a struggle to find solutions. I guess I think of that question from a teaching point of view, and the hardest thing to master, in my opinion, is finding the right way to convey the message to someone else so that they can understand what you're talking about. Because you know, there's different ways of doing each process for machining, but some people take to one idea better than another. But again, with some of the resources available today, you know, there's a lot of great schools with a lot of great programs, and I think a lot of the training has become more standardized. You know, they start with more of a safety content in mind, which, you know, I worked in a shop and safety was important, but not like it is today. So yeah, I think finding a good way to convey a message and communicate with other people. Communication is the key with all of this. You have a machinist who's making parts, he's working with the programmers are working with the engineers. I remember teaching one guy in the shop, and he said, we never use the prints we get from the engineering department because they're all garbage, and we told him so. And I said, well, I'm sure that endeared you to them greatly. Did you ever think of going in there and saying, you know, we could make better parts if you changed this one thing on the print. If you made this print better in this way, I could make the part faster, which would make the part cost less, which means we could ship more, which means the company would make more money, and maybe we'll all get a bonus at the end of the year. I said, next time try telling the engineer that, and then see how he wants to work with you. So communication is always the key, trying to get people to work together, find the common goal and the common good.
So what does a typical day as a machinist look like?
Well, it depends on the shop and it depends on the kind of work. Machining involves so many different aspects. I mean, there's places that are referred to as job shops, where they're basically contracted to make a part a certain way based on someone else's specifications. So in that case, you know, you're going to set up the job according to their specifications, the way they want it done, and machine it the way they want. If you're working for a company that's making their own product, you'll see more of a collaborative environment and something like that, because again, it's the common good. We're all trying to make these parts to make our own product better. So there's usually a lot more interaction, and it gives you a little more control over how the part gets done, because you can have a say in it. Whereas when you're doing job shop work, you're just doing what the customer ordered. You know, the print is your Bible, and you make it to the print, whether you like the way it's drawn or not. So a typical day, as a machinist, you're probably going to go in, and if it's a new job, you're going to set up your machine, get your fixtures on the table, get everything indicated and in place. Get your tools from the tool crib, calibrate those tools to the part that you're going to be machining, load up your program, and carefully run through it the first time. Usually, once the job has gone through once, you're pretty much able to push the button and let it go. At that point, you're relying more on your sense of sight and sense of hearing. You have to listen to the tools as they're chirping along on the part, and if they start chirping a little bit too loud, you need to do a little inspection there. So those are important things, and some of those things you can only experience and understand by doing it. I mean, you know, there's a lot of things you can learn in school, but some things you just have to be there for. I was setting up a job one time, and we're taking a first cut through this part, and normally when the tool starts making noise, your first instinct is to slow it down. And the lead man that I was with, he's screaming at me, go faster, turn it up, turn it up. And I thought, this guy's out of his mind working a die. I grabbed the dial and I turned it up faster, and he immediately quieted down. And he explained to me that what was happening was it wasn't taking enough of a cut, and it was just flopping around on the part. But as soon as we turned it up, it was taking a bigger bite, and now it had a grip, and it had nowhere to vibrate to. A concept that I would have never figured out on my own. So pay attention.
So why would you recommend being a machinist?
Oh, there's all kinds of opportunities. That's why I would recommend it. So I did a little research before I got here, and I did a search for manufacturing jobs or jobs in machining, and there was a top 10 list. And the first 3 items were CNC programmer, welding and fabrication, and CNC operator. I mean, they were the first 3 things on the list. And it gave a little more information on those, and it was very encouraging, you know, for people that are looking for jobs. You just have to be looking in the right place, because there was a Bureau of Labor Statistics analysis in 2014, and it said they expect CNC programmers as a position to grow 19%. Now, I don't know if that was 19% per year, because they were talking about a span from 2014 to 2024. But that's a pretty big growth no matter how you cut it. So I would say that's a pretty good area for people to get into. Now, also, I looked up just CNC operator, and again, it was similar. For the same span of time, they were talking about a 10% growth industry. And I tell you, I've been in a lot of machine shops, and you know, you always get in that discussion of how's business and how are things going. And one of the things that always comes up is they just can't get enough good people. So I'm always leery when people say there aren't any jobs out there. I just say, hey, you're not looking in the right place, because there are opportunities. It said that the average salary for a CNC programmer was just shy of $50,000 a year. That's just average. So, I mean, you know, some of these guys are making $75,000 a year programming CNC machines, and that ain't too shabby. So the opportunities are there, and I think people just need to get used to redirecting their focus, because CNC programming, you know, could be working in a shop programming a CNC machine, but it could take you in so many other directions. You could go to work for a company that makes machines like I did, or you can work for a company that sells machines, and you could be the guy that goes out into the field and works with customers. And I'll tell you, that is the best thing in the world, to get into some of these shops and work on some of these projects. I can't tell you how many times I was in a shop and we were making some crazy looking part, and you say, yeah, but what is it? Oh, this is the turret for the M1 tank. It's like, wow, really? Let me touch it. Wow, this is the nose cone for the guided missile. This is where the optics go. Really? Wow, cool. Oh, this is the brand new inline skate. It's not even on the market yet. Wow. So, you know, there's just so many opportunities out there when you're in the manufacturing trades, because everything has to be made somewhere. There isn't a single object that you come in contact with in your daily life that isn't somehow affected by a machinist and a machine tool. So when you put it in those terms, opportunities abound.
So in your opinion, is it challenging?
Oh, very challenging. Every day. You never know what's going to, you know, come up in the process of making a part, and some of the things you think are going to be simple aren't going to be simple, and some of the things you think are going to be difficult are going to be just the opposite. But yeah, there's always some new challenge, because nowadays things are getting smaller. There's all these new materials that are coming about, and finding new ways to machine them, and new ways to process and handle and hold. You know, you look at things like your iPhone. You know, those little cases, those are machined. Those are made on a CNC machine. They're not just stamped or formed or cast. So when you look at something that's that small and that thin and that light, just finding the right way to hold it so you don't crush it when you're machining it. Challenges abound.
So how did you learn machining skills?
Oh, definitely. Well, in the research that I did before I came here, I searched around for jobs. I found out that there was a lot of online training courses. So you can, get some kind of an associate's degree and certification through online facilities. But I strongly encourage you to go to your local technical school and find out what they have to offer. Obviously, with something like CNC machining, you have to get on the machine and you have to make parts. But there are a lot of courses you're going to take, like the safety that I mentioned before. Everyone has to take the safety course. You have to learn about PPE, personal protection equipment, and safety glasses and hearing protection. And I went to get a job teaching a CAM product at the community college. And I had to take this safety training course first, and it's like, wow, really? Okay. I've been doing this for, 25 years, but I'll take your course. That's fine with me. But I learned things, and they were important things. And there seems to be a lot of sources and a lot of avenues to learn about becoming a machinist. Certainly a lot more than when I started. When I started, you learned how to be a machinist by getting a job in a machine shop and falling in with the right group and hanging on for dear life in some cases. But certainly contact your local community college and see what they have to offer. I know one of the guys I work with teaches at Portland Community College. He teaches fusion. And every now and then I go in and do a little 1-hour bit about CAM, the CAM side of our Fusion 360 product. And I just did it the other day, and I was really impressed with the people that were in his class and how diverse they were. It was such a wide group of people, and some of them were working in shops, and some of them are, learning for the fun of it, and some of them are learning because it's part of a bigger degree that they want to get. But it was a nice facility, nice classroom, and they had nice equipment to use. So I strongly encourage you to check out your local community college first. And depending on what your schedule is, if you're an older individual, you're working a 40-hour week, online classes work for a lot of people too. But to be a machinist, you have to make chips. So you have to get on that machine at some point.
So what are your thoughts on trade-type education vanishing from schools?
Well, I don't know if that's really true. When I was living in Arizona, I had a job with the community college as a recruiter. And I went around to a lot of the high schools to tell them about careers in engineering and design and things like that. And I was pretty surprised at how well equipped some of their labs were. There were high schools that had little tabletop CNC machines and 3D printers. And this was, 5 years ago. So I guess it really just depends on the school. And it would be nice if more parents would get involved and see the importance of things like this. I guess a good sports program is nice because it brings people together, and sports are something that's supposed to promote teamwork. I'm not a big sports fan, can you tell? But I think these kinds of skills where the high school has a wood shop or a metal shop where people can actually go make something, there's nothing better than the pride of getting your hands on something and building it yourself and taking it and showing it to other people and say, look, I did this. So I know there seems to be a decline in a lot of programs at a lot of schools. I'm sad to hear that they're dropping band programs because I think music is important, because music, manufacturing, mathematics is at the core of a lot of this stuff. And not that you have to be good at math, because we're all walking around with supercomputers in our pocket, basically. We have the information of the world available at our fingertips. But it is sad that some schools are dropping some of their programs.
So will machinist type skills be eliminated as CAD/CAM software becomes more advanced?
Never. Never. Won't happen. There's always going to have to be that person that says, you're holding that wrong. You have the wrong tool. You need to do this way because there are reasons for this. And there are new types of processes that are coming about too, which will require new ways of thinking for machining. Autodesk is involved in all different aspects of design and manufacture. And one of the things they're doing is they have some software that will evaluate a part and figure out if the part can be lighter but still maintain its structural integrity. So a lot of these formulas that they're looking at to do this are based on things like the shape of a bone or the inside of a bone and how it's honeycombed and things like that, how that honeycomb shape makes things stronger. So with those processes, they're making some things that can't be machined on a traditional machine. But that's where 3D printers and now 3D metal printing is coming into play, or what they're calling additive manufacturing. We never called machining subtractive manufacturing, but we call it subtractive manufacturing now because now we have additive manufacturing. So machinist skills will always be in demand because even when those special parts are 3D printed, someone's going to have to machine this surface flat and drill this hole round and do all the nice things that make that special custom bracket fit in place.
So what would you say is different between a small desktop mill like we use versus a large Bridgeport mill?
Oh, there's things much beyond the Bridgeport mill too. And that's a conversation that comes up in our office because I work with a bunch of engineers and we're working with some of this really cool software. So they all want to have a CNC at home in their garage. And sometimes they can't understand why this machine is $500 and this one is $5,000 and this one is $50,000 and this one is $500,000. Is it just because they're bigger? No, it's not just because they're bigger. Obviously, when they get bigger, they become more sturdy, and in most cases, they become more accurate. So bigger parts, or bigger machines, you can make bigger parts with better tolerances. That commands more money, therefore the machine itself is more expensive. But the desktop machines that you're using in your shop, one simple thing that it comes down to is the feedback system for how the tables and how the heads move. The controller has to know where it's at. It's telling it to go to a certain position, but it doesn't necessarily know if it got there or not on a less expensive machine because it's using something called a stepper motor. And that is in an open loop system. So as an example, if you said, I need to move 1 inch, the control might say, okay, I need to pulse the motor 50 times to make it move 1 inch. So it pulses 50 times and it says, you should be at 1 inch. On the more expensive machine, they'll have a glass scale on the table that's giving direct feedback to the control. Or they'll have a rotary encoder on a ball screw that tells you exactly where that ball screw is. So when it says go to 1 inch, it knows exactly when it's exactly at 1 inch within 30 microns. So there's a big difference between the machines. But here's the real big difference for the person who wants to buy one is, what are you going to make? I don't need to split the atom. Most cases I'm machining, a piece of plastic. Lately I've been machining wood. If the room gets a little humid, that wood is going to grow anyways. So I don't need that much accuracy for what I'm doing. Mostly what you need is repeatability. If I want to make 10 of these, I want them to be the same. If they're all off by a little bit, it's pretty okay. As long as they're all off by the same amount, the same way. That's kind of a big difference between the little machines and the big machines.
So can you share a bit about the conversion process for making a Bridgeport mill have CNC capability?
Sure. Actually, I worked for a company for 10 years, and that was their big thing. As I mentioned, I started off working for a company that made big CNC machines. And when I interviewed with the control company, it was a place called Analam Electronics, who unfortunately is no longer with us. But when I went on the interview, he said, yeah, what we do is we make this controller and we provide the ball screws and the brackets so that someone can put this on a Bridgeport and turn their Bridgeport into a CNC machine. And I thought, and I asked him, I said, so why would somebody want to do that? And he said, because it's only $20,000 versus $200,000 for a CNC mill. I said, that's a pretty good reason. So that, at the time, was the low-cost everyman's CNC. To be able to take your existing Bridgeport and put a control on it was a big deal. But yeah, they provided a kit. Most cases we had our installers put the kit on there. But it consisted of a new set of ball screws for the machine. The ball screws are actually, they look like a screw, and they connect to the table and they drive the table back and forth. And there was a motor that drove the screw, and there was a rotary encoder on the end of the motor. So that would count how many revolutions it had made, so it knew where the position was. So even though this was a $20,000 low-cost system, it was still a closed-loop feedback. It was pretty accurate. They could hold plus or minus a half a thousandths, which, you know, for a Bridgeport, that's pretty darn good. So that package would be mounted along with the electronics cabinet, and they'd periodically come out with software updates, which were not software updates like you imagine today, where we just, you know, download it over the wire, pull out a board, put in a new board with new EPROMs on it, and update it. But yeah, it was a nice kit. It was something that could be installed in a couple days, and it really brought CNC to just about every shop. Everyone was able to get it affordably, you know, even those places that couldn't afford to go out and buy a $200,000 CNC.
So moving over to some of your video work, how do you make tutorial videos, and do you have any tips to offer other video producers?
Sure. Yeah, producing training content, making videos is something I ran my own company for 12 years doing that. And I produced products that I sold under my own product name, and also things that I produced for other companies for their educational websites. And one of the main products I use to do that is a product called Camtasia. I think everybody is probably familiar with it. It's pretty common. It allows you to capture what you're doing on the screen, and you know, you can add some overlay graphics on top of that, similar to what I'm sure we're going to be doing with some of this video. And I guess if I was going to give somebody advice on how to make a video, I would say relax and don't fidget a lot. You have to remember, when you're capturing something on the screen, the person watching the video sees your little mouse pointer on the screen. So that little mouse pointer, that's you. So as you're talking to them, they're watching you move around the screen. Now, I know some people get this nervous habit where when they're talking, they'll take their mouse and they'll move their hand back and forth. And so the guy's watching what's on the screen, and yet the little arrow's going in a circle. It's not good for a well-planned lesson. So don't fidget. Also, if you find that you have to edit the video, which we'll probably have to do with this, you don't want to have something that's called a jump shot, where it goes from one scene to another scene. So if you're holding your cursor in one place and you talk and you say something wrong, you can just say something right and cut out the bad section. But if your cursor was over here, and suddenly your cursor's over here, that's not a good thing. So those are important. Take your time. Some people think that, you know, we got to get these sentences out, and we're going to say this as fast as we can because we want to get this done, and we want to show you how exciting it is. And when you're editing that, what I look at is the waveform. So you'll see this squiggly waveform of the audio. And if I said one word that was bad, it's hard to see where that one word is if your waveform is just one big blob. But if you say your words with slight pauses in between, it makes it much easier to edit the video. So those are important things. Try not to stay on a static screen for too long. Make something happen, even if you just have to pop up a quick image to maybe illustrate your point. Staring at the same blank screen with nothing happening for, more than 30 seconds can be a bad thing. But video is a great way to convey a message. I call it short attention span theater, because people really have a hard time focusing on something. If you give somebody something to read, if I handed you a page and said, here, read this, you'd say, what is it? In other words, just tell me what it is, because I really don't want to read this, or I'll wait till it comes out at the theater in a movie. So keep your videos short, try and get to the point, but I think a lot of people appreciate being able to watch something in a video and get to a point quickly, rather than having to read a manual on how something works. Even though when I write the written documentation for Fusion 360, it is a work of art. And I strongly encourage you to read every word that I write.
So mentioning Fusion 360, I was wondering what the benefits of using Fusion 360 over other camera-related software is.
That's a real good question. For years, it's been CAD, CAM software. You bought a CAD product over here and you bought a CAM product over here. And they had the ability to share files with each other in some way, but always through some kind of a translation. And the more you translate something, sometimes the worse it can be. So one of the big advantages that Fusion 360 offers is it's a fully integrated system. You have state-of-the-art engineering class modeling built into a package that also has state-of-the-art CAM software, and it's using some of the same functionality that some of the other CAM products have licensed. The core team that developed our CAM software developed the driving engine that other systems have licensed. So, it's a very sophisticated product, and it allows you to cover so many different things. And then there were these other aspects of Fusion that I really didn't even think of. I mean, when I started to work at Autodesk, I saw it as CAD and CAM. You made a model, and then you machined the model, and then you created G-code, and you sent the G-code out to the machine. But we have all these different workspaces in Fusion, and there's animation. So you could say, okay, I want to take, I made this model or this assembly that is maybe 5 or 6 different parts. And I can go to the animation section and say, yeah, I want to be able to pull these apart this way, and I want it timed a certain way. So when you see those exploded view things, and they go apart and they come back together, I mean, Fusion is like $495. The CAM software that I used to sell, just the CAM part of it was $13,000. So to have that CAM capability and all that CAD capability, oh, and I can do animations. Oh, and I can do photorealistic rendering. Oh, and it has sheet metal bending capability. Oh, and I can do drafted parts. Oh, we bought this electronics company. Now you can design your electronics module and see how it's going to fit inside the case of your model before you send your model over to your CAM software to make the molds. I mean, we have all these components that we're putting together into this single source product that people can use, and it's so affordable that anybody can get their hands on it and use it. And the best part is, if you're a student or an educator, or if you're a startup company making less than $100,000 a year, Fusion is free because we want you to make anything. That's our slogan, make anything. So, you know, we want people to go out and share their ideas. You know, people are walking around with these great ideas in their head, and we want to help them get it out of their head and get it into some form that they can communicate with other people. And Fusion is just changing the way the world works for that. One of the biggest things about Fusion that makes it different is that it's cloud-based. With the other products I used to sell, whenever I'd go to an industrial show, you know, I'd have to be prepared to do a demo. So the week before, I would have to take all of my little files, all my demo files and my tool libraries and all my special little things that someone might want to see, and I'd have to put it on a CD, yes, a CD, or on a flash drive, and take it with me to the show, and I'd have to put that on the computer that I was using. But with Fusion, everything is up in the cloud. So I can walk up to your computer, log in with my profile, and all my stuff is there. And it doesn't matter what computer I get on, because it works on a PC, works on a Mac, and that's probably an industry first as far as I'm aware. So Fusion is an amazing product, and Autodesk is an amazing company. The things they do are just astounding. So just to give you an idea of some of the other things they do, if I can spread out a little bit. I didn't realize that we were involved in, I'm going to say making movies. We don't actually make movies, but we make software that is used to do a lot of the animations and a lot of the things that you see in everyday movies. So if you've seen Guardians of the Galaxies, which you'd have to live under a rock to not have seen it, but a lot of the stuff that's in there was created, a lot of those animations and some of those characters are created using Autodesk software. Game of Thrones, the dragons. I mean, if you've seen those dragons are cool. You can bet every time I'm standing with somebody and I see a picture of those dragons, like a company I work for, we do stuff like that. So we're involved in all these things. So when we say make anything, we mean make anything, anything. So yeah, it's a great company. I'm really proud of it.
So oftentimes when making parts, there can be a disconnect between designers and machinists. What practices should design engineers practice in order to make a machinist's life easier?
Oh, that's another good question. When you're modeling a part, they show you all these really neat things to make the part look pretty. A lot of times they'll want to put little chamfers on all the edges or little fillets in all the corners, and it makes everything look smooth and blended and nice. But when you put a 1/16 radius fillet on the inside corner of a wall that's 6 inches deep, it means he has to have a tool with a very tiny radius to fit in that corner, which might mean he has to have a custom tool made. So a simple thing like removing all those little fillets that, I mean sometimes the fillet may serve an actual purpose in how the part works, and then it has to be there. But if the fillet is only there for cosmetic reasons, you've drastically increased the cost to make that part because you put chamfers and bevels and radii in all the corners. So I've seen cases where, you know, I've talked to the customer and said, you know, does it have to be like this? And at first it's like, well, yeah, that's the way I designed it. That's my part. And then you start to explain that, well, because you have these things, we have to order special tooling. And every time I have to order something special, you have to pay for it. And you increase the time it takes me to do this. So I could use the tooling I have and have this ready for you by the end of the day if we take all that stuff out. Or I can have this part to you next month after I order my special tooling. Oh, well, suddenly I need it right away, and those little fillets, they don't mean anything. So that's an important thing, is try and look at your design from a viewpoint of how it needs to be made. And if you're not sure, certainly walk out to the machinist. If you're the engineer, walk out to the machinist. Or if you're the machinist, go in and talk to the engineer and say, you know, these things could be improved to streamline the manufacturing process. Don't just go in and tell him he did it wrong. Go in and say, boy, this could be made quicker and better if we did these little things. How about it, buddy? Let's work together. So, those kind of things.
So when taking on a machining project, what types of things do you need to think through? Are there certain steps you tend to take for most projects?
It's always the fixturing. It always comes down to the fixturing. Anytime someone talks to me about making a part, it's always, oh, well, it's just a simple little thing. Yeah, it's you know, 1 inch by 2 inches, and it's 1/8 of an inch thick. How do you think we should hold on to that? So when something gets small and thin and light, it always comes down to how you're going to hold and fixture the part. And it's really no different with big parts, but it's more noticeable with little parts. But it always comes down to how you're going to hold it. It's the most critical thing in any manufacturing process. It's the first thing you have to look at. It's the first thing I always look at. Because if you can't hold it, you can't machine it. After that, what kind of materials is the part going to be made of? Will I need any special tooling? Is the material so hard that I'll require special cutting fluids? And what are the requirements, again, what are the safety requirements for those cutting fluids? You know, if those fluids get airborne, what are the ramifications? If those cutting fluids sit in a tank too long and get stagnant and moldy, what are the ramifications? There's a lot of things to consider in the process.
Do you have any preferences between rapid prototyping and detailed CAD design? Is there a place for both, or is one approach preferable?
Oh, rapid prototyping is the most wonderful thing in the world. If you have an opportunity to 3D print your part before you're going to make it, always do it. Always. I had to modify this bass guitar that I had because the bridge was, I didn't like it. So I knew that if I just made an extension for the backside, it would solve all my problems. So I modeled it up in Fusion, and I looked at it and analyzed how it was going to fit and how things were going to come together, and then I sent it to the 3D printer, and then I could hold it up to the piece that it was going to match to and see how it was going to fit, and then I was sure that I was on the right track. Now I can take an expensive piece of material and invest the time that it takes to cut a piece of metal properly and get the right tolerances and finishes. But if you can rapid prototype on some kind of a 3D printer before you go to the cutting process, always do it, because there's little things that you're going to find that, oh, I didn't make this wide enough, or I didn't make this long enough. And you know, when you're doing it all inside the same program, like with Fusion, it's real easy to just go and say, well, I need to move this face out 20 thousandths. And because it's all in the same environment, the toolpath is attached to the model. It's associative. As the model changes, the toolpath will update automatically. So you kind of, once you've done your toolpath on that, any changes you make, the toolpath comes for free afterwards.
So what is the Machinery's Handbook, and what is it used for?
Machinery's Handbook is the source of all knowledge in the universe for machinists. There is so much stuff in there. When I first started working in the machine shop, one of the guys says, you have to get a Machinery's Handbook. I was like, what for? He says, just don't worry about it. You're going to need it. And I got it. And I found just like a couple of chapters, you know, like 5 pages here and 5 pages there and 5 pages there, that were extremely valuable to me. And that's in a book that's this thick. But some time later, I actually started to just sit down and page through the book. I couldn't believe the information that was in there. It's just the source of all manufacturing knowledge. Anything that has to be made, any standards for sizes and threads and measurements, and just, oh, if you're going to be a machinist, you're going to have to get the Machinery's Handbook. Of course, I'm sure it's available now in PDF form, but I don't know, there's something about holding the book in your hand and being able to flip through it. I don't think people are as inclined to flip through a PDF. I think you're going to search for what you want, get in and get it and get out. But with a book, you know, you could flip through it and say, well, that's an interesting illustration. What are they talking about there? And read about and learn about something that maybe you didn't know before. There used to be a companion book. It was the Machinery's Handbook and then the Machinery's Handbook Book of Formulas. And I got both. And I have to say, I've only used the formula book a couple of times. But, you know, it's the extension to the Book of All Knowledge. So certainly worthwhile. Even if you're not going to be a machinist, if you like to make things and you have to know about sizes and nuts and bolts and screws and pins and locators, it's worth getting.
So as a machinist, what is the best practice for creating a straight interior corner? Would you use something like the method shown?
Well, you could, because that will allow you to fit a square piece inside that edge. But you're going all the way up and you're kind of burying the tool when you do that. Another way would be to actually just drill out the corner first. Or you could take the end mill that you're using and drill that corner. If you're just going to use a drill on the corner, you want to drill it before you mill it, because otherwise the drill isn't going to have anything to grab onto. It'll walk all over the place. So you drill the hole first, and then when you machine out the corner, you'll get a full clearance for the piece that's going to fit in there. There's another way to do it where if you just go from the corner out at 45 degrees, the radius of the tool that you're going to use, and make that the center point for your drill, then you won't have to cut as far into the part and you'll still get the clearance that you need. But that's always been the trickiest part of design and manufacturing is, you know, somebody draws this, they want to fit something square into an area that, you know, I just drove a round tool through there. A round tool is always going to leave a radius, and you can only get so small with your tools and get the radius down to a certain size, but certainly never a sharp corner. Square tools are hard to find. So those are the two methods that I would recommend, is just drill right on the corner or create a point at 45 degrees just inside of that corner, and that'll give you adequate clearance. You know, it really just depends on structurally how much digging out that corner is going to affect the part. You know, if it won't matter and you've got plenty of room, just drill the hole in the corner. But if you want to keep as much meat as possible, then do the 45-degree intersection and do it that way.
So since earlier you introduced the topic of safety, what do you look for safety in a shop?
In a shop, the thing that always impresses me the most is if it's well lit. An environment should always be well lit so that you can see what you're doing. Clean. A shop should always be clean, because oil on the floor, chips, those are all big safety hazards that you have to watch out for. Certainly you should always wear your safety glasses. If there's a lot of noise, you should wear your hearing protection. If you're in any shop now, they'll always have some poster on the wall that's telling you something that you should be careful about. And most of the time those things are pretty much common sense. So probably the best safety tool that you have is your brain. Try and keep your hands and fingers out of moving parts, and think about things before you do them. And if you're not sure, ask someone. It's the most important thing about safety. And when that end mill is spinning around in the spindle, no matter how mesmerizing it looks, don't touch it. It will cut your finger.
Well, that's all the time we have for now. Thank you for joining us, Mike.
Thank you for having me, Stephen. I really enjoyed the opportunity to speak with you today.
So up next, we'll be having one of our tutorial videos, so stay tuned for that.